Hello friends, welcome back to my YouTube channel. Today in this video lecture, I will be discussing a numerical. This is part number 7 and I have been talking about stage-wise leaching. In part number 6, I had discussed the theoretical concepts of multistage cross-current leaching, and today I will discuss a numerical that is based on multistage cross-current leaching. So the numerical is based on my discussion in part number 6. I'm giving link to the playlist which has all my videos on leaching, and I hope you must have seen part number 6 on which the numerical is based. So let us start the discussion. To begin with, let us look at the numerical statement which we will be solving. Caustic soda is being made by treatment of slake lime, that is CaOH twice, with a solution of sodium carbonate. The resulting slurry, it consists of particles of calcium carbonate, that is CaCO3, suspended in a 10% solution of sodium hydroxide, that is NaOH. And the slurry contains 0.125 kg of suspended solids per kg of solution. This is settled. Here sodium hydroxide solution is withdrawn and replaced with equal weight of water, and the mixture is thoroughly agitated. After repetition of this procedure 2 times, what fraction of the original NaOH in the slurry remains unrecovered? So let us understand what is given in the numerical statement. So caustic soda, that is NaOH, sodium hydroxide, caustic soda, it is being made by treatment of slake lime, which is nothing but calcium hydroxide, CaOH twice, with a solution of sodium carbonate. So basically a chemical reaction is carried out between calcium hydroxide and sodium hydroxide, which produces calcium carbonate. The resulting slurry of the reaction, after the reaction is completed, the resulting slurry is consisting of particles of calcium carbonate, the product that is formed, CaCO3, and these particles, they are suspended in a 10% solution of sodium hydroxide, that is NaOH, and the slurry has a concentration of 0.125 kg of suspended solids per kg of solution. Now this slurry is then allowed to settle, and then the clear sodium hydroxide solution is withdrawn, and after withdrawing sodium hydroxide solution from the slurry, an equal weight of water is replaced with it, and then the mixture is thoroughly agitated, and then the resulting clear solution is separated from it. So this is repeated. After repetition of this is repeated for 2 times. That is removing of the clear sodium hydroxide solution and then replacing it with equal weight of water. This is repeated for 2 times. So at the end of this operation, what fraction of the original NaOH in the slurry remains unrecovered? So we are supposed to report what fraction of the original NaOH solution remains unrecovered. So at the end we are going to represent this number, fraction of the original NaOH in the slurry that remains unrecovered. Okay, so let us move ahead and solve this. First of all, along with this information, the equilibrium data is also given. The data has this parameters: x, small x, which is weight fraction of NaOH in the clear solution. Then you have small y, which is weight fraction of NaOH in the solution of the settled sludge. And capital N is kg of calcium carbonate per kg of solution in the settled sludge. So we have different values of these three parameters or three quantities: x, y, and capital N. X is weight fraction of NaOH in the clear solution. Y is weight fraction of NaOH in the solution of the settled sludge. And N is kg of calcium carbonate per kg of solution in the settled sludge. So we have different values for these three quantities: different values of x, different values of y, and different values of N. Now if you look at N is kg of calcium carbonate per kg of solution in the settled sludge. So we have N values for settled sludge only. That means there are no solids in the clear solution. Whatever solids are there, all the solids, they are in the settled sludge. That's why we don't have values of N for the clear solution. And what is the meaning of that? N for clear solution is 0. All N's corresponding to clear solution, all N's corresponding to these values in the clear solution, they are 0. We have only N values in the settled sludge. All N values in the clear solution, they are 0. Okay. Why I'm telling this to you? Because this will be useful for us while plotting the graph. So we have the equilibrium data. Equilibrium data is given in terms of small x, which is weight fraction of NaOH in clear solution, small y, which is weight fraction of NaOH in solution of the settled sludge. In the solution that is associated with the settled sludge, or the solution that remains in the settled sludge, weight fraction of NaOH in that settled sludge in the solution of the settled sludge is y. You have different values of y, and then you have different values of N, which is kg of CaCO3, that is kg of calcium carbonate per kg of solution in the settled sludge. So with this information and with this data given to us, let us find out the fraction of NaOH that remains unrecovered. Okay, first let us look at the given data. The process is it is production of caustic soda, that is sodium hydroxide, which has a chemical formula of NaOH, you know that. Production of caustic soda by a chemical reaction between sodium carbonate, that is Na2CO3, and slaked lime, that is calcium hydroxide, CaOH twice. And the chemical reaction involved is Na2CO3 plus CaOH twice. It gives us 2 NaOH plus CaCO3. That is the chemical reaction. And CaCO3 is formed in a precipitate of CaCO3 is formed during the reaction. And this reaction results in a slurry of calcium carbonate in a solution of NaOH. That is the process. And the task is to recover this sodium hydroxide from that slurry. So if you have to show it pictorially, you can understand in this way. So you have a tank and you are adding sodium carbonate to it, and then the sodium carbonate solution to it, and then you are adding the slake line, that is CaOH twice. So there will be a chemical reaction between these two, which will produce calcium carbonate and sodium hydroxide. So after the slurry is formed, after the reaction is completed, and you have a slurry of solid suspended in NaOH solution, then when you allow the slurry to settle, it will settle into two layers. The bottom layer is the sludge containing solids, and the top layer is the clear solution, which you are going to remove. This is clear solution of NaOH, clear NaOH solution. And what information is given to us? This solution, the solution that is formed, it is containing 10% NaOH. 10% NaOH, that is solution of NaOH in water, and it is containing 10% of NaOH in it. And you have the sludge. And then you are going to separate the clear solution. So you are left with the sludge. So the entire operation over here, you can call it as the first stage in leaching. So in the first stage, you have separated the clear NaOH solution that is formed in the slurry, and the solution is containing 10% NaOH in it, and you are removing it. So you can call this as first stage leaching. Now in the second stage, what you are doing, you are adding fresh pure water to the slurry or to the sludge, and this water is nothing but the solvent in the second stage. So in this case, water will be the solvent, and it will be used to leach out the NaOH from the sludge. So you can call this as, and then after the leaching is completed, the clear solution is again separated. Clear solution is nothing but solution of NaOH. So this is the second stage. And in the third stage, you are transferring the slurry. In the third stage, the sludge is again contacted with a fresh batch of water, and then the clear solution is removed. So this is the third stage. You can call it as the third stage of leaching in this case. And you please remember, whatever clear solution is removed in first stage, the weight of whatever clear solution you would remove in the first stage, water of whose weight is equal to that removed solution, it is added in the second stage. And whatever clear solution you remove at the end of second stage, water equivalent to the weight of that clear solution is added in the third stage. That means in second stage, water whose weight is equal to the weight of clear solution that is removed in first stage, it is added in second stage. And in the third stage, water whose weight is equal to the weight of clear solution that is removed in second stage, it is added as a solvent in the third stage. So if you have to identify the three components in this process, you can easily identify. In this case, C, which as per our notation is the solute that is to be recovered by leaching. So in this case, it is NaOH, that is sodium hydroxide. And then B, the insoluble solid, in this case is calcium carbonate. And the solvent that you are using, it is water. So the three components that you can identify for this particular problem, C is the solute to be removed, and it is sodium hydroxide in this case. B, the insoluble solids involved, in this case these are solids, solid particles of calcium carbonate, and the solvent that you use is water, which we denote by A, capital A. So at the end of this particular discussion, now you know what is the process. So it is a simple 3-stage cross-current leaching operation in which NaOH is to be recovered by using water as solvent. So that is what is given to us in the numerical statement. Okay, now let us solve the numerical. So I will check the schematic diagram in our discussion so that you can understand it. Now, since we don't know the amount of, we don't know feed as such. So that's why we have to start with a basis in this particular case. And I'm going to choose a basis in this way. I'm going to consider, or I will be considering 100 kg of NaOH solution in the original mixture. That means I'm considering 100 kg of clear solution that is obtained in the first stage. Clear solution that you remove from the slurry after the reaction takes place between Na2CO3 and CaOH twice. So that clear solution, I am assuming it to be 100 kg. So 100 kg of NaOH solution in the original mixture. So as per our notation, this is nothing but M1, which is kg of A plus kg of C in the mixture that is formed in first stage. So now I am starting with M1 known to me. How it is known? I have chosen a basis. M1 is 100 kg. You just try to understand 100 kg of NaOH solution that is formed in the first stage. So that is the basis. That is my basis. 100 kg of NaOH solution in the original mixture. And that is nothing but M1. What is M1? This is kg of A plus what is M1? How do you define M1? This is kg of A plus kg of C in the mixture that is formed in first stage. And we are starting with it. We are saying that there is 100 kg of NaOH solution in the original mixture that is formed in the first stage. So we will do our calculation with this basis. So let us do that. Let me erase it. So this 100 kg, it is containing 10% of NaOH, which is C, and the remaining 90% could be water, NaOH solution. Remaining 90% is water. So first step with this information, in the first step we will find out Ym1 and Nm1. What is Ym1? Ym1 is weight fraction of NaOH in the solution. Weight fraction of NaOH in the solution, in the mixture. And Nm1 is weight fraction of B in the mixture. Weight fraction of C in the mixture on B free basis. Weight fraction of B in the mixture on B free basis. So in order to know what are this Ym1 and Nm1, you have to refer my previous video on this topic, multistage cross current leaching. So for that, we know kg of C in the mixture. Now the mixture is containing 10% of NaOH in it. So it will be 0.1 into 100. We have started with the basis of 100 kg. So 0.1 into 100, that is 10. And then kg of A in the mixture is remaining thing, 90%. 90% of the mixture is E. So it would be 0.9 into 100, that is 9. So now kg of C in the mixture is known to me and kg of A in the mixture is known to me. I can find out Ym1 and then I can find out Nm1. So ym1 is nothing but kg of C per kg of kgc per kgc divided by kgc plus kga in the mixture, and we know this too over here. So therefore ym1 will be equal to 10. Kg of C is 10 and kg of A is 90. So ym1 will be equal to 10 upon 10 plus 90. That gives ym1 as 10 upon 100. That is ym1 is equal to 0.1. Now the original mixture as it is given in the numerical statement, it contains 0.125 kg CaCO3 per kg solution. This solution is nothing but solution of A and C, kg of A plus kg of C. So this is kg of B per kg of A plus kg of C. So this quantity is nothing but NM1 itself. So that is NM1 is directly given to us in the statement. So NM1 is equal to 0.125. So in this way, we now know ym1, which is 0.1, and we know NM1, which is 0.125. Let us move ahead. Then we also need to know what is kg of B in the original mixture. So let us find out. So NM1 is now known to us. It is 0.125, and you know how NM1 is defined. NM1 is kg of B per kg of C plus kg of A in the mixture. This is NM1, which is 0.125. That is known to us. So it is kg of C is 10. It is known to us. Kg of A is 90. So kg of B divided by 90 plus 10 plus 90 is equal to 0.125. That is kg of B divided by 100 is equal to 0.125. That is kg of B is equal to 0.125 into 100. That is kg of B is equal to 12.5 kg. So this is the quantity of insoluble solid that is present in the system, and this quantity is not going to change. It will remain constant. So now we know. Okay, then next we need to plot the required graphs. So first graph is when on the x-axis we will be plotting x and y, the given values. We have to use the given data as it is, given equilibrium data as it is. There is no need of doing any conversion with that data. So xy given to us, we will plot on the x-axis, and n we are going to plot on the y-axis. And as I told you earlier, we have n values for the sludge, n values for the clear solution, they are 0. So n x versus x curve, it will be coinciding with the x-axis. The curve that we will be getting, it will be ny versus y, that is values of n in the sludge or values of n in the underflow. So these are ny values. Actually we are plotting ny versus y, and x values, they will be simply plotted on the x-axis, because all n x, all n's in the clear solution, they are 0. So let us do it. So that's why y values will be plotted against the given n values, and you are going to get this black curve. Whereas since n corresponding to the clear solution are 0, all n's, so simply x values, corresponding x values, they are plotted on x-axis. So you get these two curves. And then since, if you remember, we got ym1 as 0.1. So I need to extend this curve so that this 0.1 is covered in that way. And then one more task I will do. I will connect the corresponding x and y values with tie lines because the x and y values that are given to us, those are equilibrium values. So they will be connected, or they have to connected with tie lines. So what now I'm drawing, these are tie lines, and these are given tie lines. These are given tie lines. And then we will also need to plot x versus y graph, because that will be used for plotting the desired tie line. So x is in that x is small x is plotted on the x-axis, and small y is plotted on the y-axis, and you get this curve. And as I said earlier, I need to extend this graph. So I'm extending it. Same thing I will do with the x and x versus x curve. And this graph also needs to be extended in order to cover point 1, because ym1 is point 1. So that's why I'm extending it. So this part of the curve is not given to us. I have drawn it approximately by considering the given data. And we are going to use this in our calculation. We need to extend this graph in this particular numerical in order to cover point 1, because ym1 we calculated it earlier. It has it is 0.1, and in order to get that, we need to extend the curve on this graph and also on the other. First, we will do calculations for first stage. So we will follow those calculations on this graph. First thing is, we have to locate m1. Now, in this particular numerical, quantity of m1 is directly known to us. We have chosen that as our basis. But in other numericals, you may have to first find out m1, and then by material balance equations, and then after that you will have to locate point m1. Now over here, since m1, quantity of m1 is known to me, now I'll directly go to locating point m1 on this graph. So this point m1, it will be located at ym1, nm1. Both are known to us. ym1 is 0.1 and nm1 is 0.125. So either one of these two values can be used to locate point m1. So let us use the value of nm1. So I will locate. Okay, in this case, since we don't know f, yf, we don't know. Here in this particular numerical, we don't have yf and quantity of f, that is quantity of feet. So for that, in this particular numerical, let me correct myself, we need to use both ym1 and nm. Because point m1 will be located on the line f s0. But since we are not drawing the line f s0 in this particular numerical, because we already know about the mixture that is formed, so that we have considered to be stage number 1, the formation of mixture after the chemical reaction is completed. That is first stage, and we have chosen the quantity of m1 as our basis. So the point is, we need to use, in this particular case, we need to use both ym1 and nm1 to locate point m1. So ym1 is 0.1, nm1 is 0.125, that is 0.125, and then I will get this point, which has coordinates of 0.1 and 0.125. So this will be my point m1. So this is how in this particular numerical you have to locate point m1. Let us move on it. Next task is, once point m1 is located, we have to draw a tie line that passes through m1. So for that, we will be using the equilibrium curve. And what you do, you have to draw the trial line by trial and error. So what is the approach? Draw a tie line through m1 that is parallel to the nearest given tie line, and then with the help of this equilibrium diagram, you adjust the position of the tie line in order to get the desired tie line. The desired tie line will be the one whose endpoints will represent equilibrium concentrations. If you simply draw a tie line that is parallel to the nearest given tie line, it may not be the desired tie line. It may not have ends that are in equilibrium with each other, and that's why we have to adjust the tie line. So if I do that, I draw a tie line that is parallel to the nearest tie line, and then adjust its position in order to make sure that its endpoints represent equilibrium concentrations. I get these values. So I get x 0.1, and the value that is in equilibrium with 0.1 y value, it is 0.099. So y 0.099, x 0.1, this will be the endpoints of my desired tie lines, and I will draw the tie line. So this end of the tie line will represent concentration in the underflow. So I will represent it as U1. This end will represent concentration in the overflow, and I will represent it as O1. So now I have got the tie line that represents first stage in the operation. So for this tie line, x1 is 0.1, y1 is 0.099, and I also need n1 in my calculation. So I will read y coordinate of this 0.1, and y coordinate for this 0.1 is n1, and it is 0.481. So at the end of this particular calculation, now I know value of x1, I know value of y1, and I know value of n1. Okay, so let us continue with the calculations for stage 1. Now next is, after knowing x1, y1 and n1, next task is to get quantities of U1, quantities of underflow in stage 1 and overflow in stage 2. So we are going to find quantities of underflow and overflow. So for that, we will use definition of N1. N1 is kg of B per kg of B divided by kg of A plus kg of C in the underflow that is obtained in stage number 1. So kg of B is known to us. We have found out earlier, that is 12.5. N1 is known to us. We just got, that is 0.481. So 0.481 is equal to 12.5 divided by kg of A plus kg of C in the underflow in stage 1. That is kg of A plus kg of C in the underflow is equal to 12.5 divided by 0.481. That is kg of A plus kg of C in the underflow is equal to 25.99. And this is nothing but the underflow, U1, quantity of underflow. That is 25.99 kg. Now we have to get quantity of overflow, that is OL. So let us find it. Let us find the quantity. For that we will use the material balance. So underflow in stage 1 plus overflow in stage 1 is the quantity of mixture. So U1 we just found out, it is 25.99 kg. M1 is the basis that with which we started, 100 kg. So 25.99 plus O1, that is equal to 100. That is O1 is equal to 100 minus 25.99. That is O1 is equal to 74.01 kg. So the quantity of overflow that is removed, the amount of quantity of clear solution that is removed from stage 1, it is 74.01. So let us move ahead. So with the calculations done for stage number 1, now let us proceed for calculations for stage 2. In stage 2, what is done? You are removing the clear solution in the first stage, and the left, whatever underflow is left, the underflow in this first stage, it is contacted with fresh solvent, and the solvent used is water. The quantity of solvent used is equal to the quantity of overflow that is removed in the first stage, and we have just found out at quantity. So S02 is equal to O1, and O1 is 74.01 kg. We just got it. That means SO2, the amount of solvent that will be used in second stage is 74.01. So with this quantity is known, let us find out M2. So M2 is U1 plus SO2. U1 we got it earlier, 25.99 kg. So M2 will be equal to 25.99 plus 74.01, and it will be 100 kg. Why this is happening? Because you are replacing equal quantity of water. After removing the clear solution, you are replacing with an equal quantity in the second stage. That's why the weight of the mixture, kg of A plus kg of C in second stage, it is coming to be 100. Then let us find out NM2. And how do you get it? NM2 is kg of B upon M2. Kg of B is 12.5, M2 we just got it. So NM2 is 12.5 divided by 100. So again NM2 is 0.125. We are getting the same. NM2 is 0.125. Now let us find out YM2. YM2 is U1 Y1 plus SO2 into X0 divided by M2. This is according to the material balance. In order to know more about it, you please watch my earlier video. So YM2 is U1 into Y1 plus S02 into X0 divided by M2. In this case, Y1 is known to us. We just found out. It is we found out it earlier. Y1 is 0.099. X0 is 0, Y0 because you are using fresh water. It is not containing any solute in it. So that's why X0 is 0. So YM2 will be equal to 25.99 into 0.099 plus 74.01 into 0 divided by 100. That is YM2 is equal to 2.57 plus 0 upon 100. That is YM2 is equal to 0.0257. So now you know NM2, you know YM2. Now you have to use them for locating point M2 on the graph. So let us do that. So again, we will use our earlier graph. Now the task is to locate point S0. Now this is the first time where you are using refresh solvent. So now we will have to locate S0 before we proceed for locating M2. So this point, it will be located at X0, N0. X0 is 0 because you are using fresh solvent. N0 is also 0 because it is not containing any solids in it. X0 is 0, N0 is 0. The reason is we are using fresh pure water as the solvent. So S0 will be located at the origin 0, 0. So this is S0. So you got S0, you have U1. So in second stage, underflow from stage 1 is mixed with fresh solvent. And how to represent this on the diagram? You can represent it by connecting points U1 and S0 with a straight line. So I'll do that. So now point U1 is connected with S0, which tells you that underflow from stage 1 is mixed with fresh solvent. And then you can go for locating point M2. Point M2 is located at YM2, NM2, both values are known to us. YM2 is 0.0257, NM2 is 0.125. Now in this particular case, you can use either one value out of this. Why it is so? Previously we needed both the values. Here you just need one value. The reason is, in this case, we know the point, the line on which the point will be lying. So if this line is known to us, we can use only one value. That is sufficient. And for simplicity, we are going to use nm2 because we have already have located nm2 0.125. So this will be the intersection of this with the line. Yes, u1 is not occurs over here. So this is nothing but point m2. So this is point m2. So this is how you can locate point m2 for the second stage. Okay, then the other important thing, we have to draw a tie line through m2. Now we need to draw a tie line through m2, and for that we need to use the equilibrium diagram, x versus y diagram. Now again, what we will do, we will draw a tie line through m2 that is parallel to the nearest given tie line, and then we will adjust the position of the tie line so that its endpoints represent concentrations that are equilibrium that are in equilibrium with each other. So if I do that, I will be having a tie line whose endpoints are 0.024 and other endpoint is 0.035. So my tie line will be having endpoints of 0.024 and 0.035. That is x, one endpoint. Endpoint on the lower curve, that is 0.024, whereas endpoint on the upper curve, that is 0.035. Again, I have found out it by trial and error. I have first drawn a tie line which is tie line through m2 which is parallel to the nearest given tie line, and then I am moving it so that the endpoints of the tie line represents equilibrium concentrations. So in that process I found out this endpoints. So I will draw a tie line. So this endpoint, this point will represent concentrations in the underflow. I'm going to represent it as U2. This endpoint represents concentrations in the overflow. I'm going to represent it as O2. The x coordinate of this point is x2. So in this case it is 0.024, and the x coordinate of this point is y2, and this is 0.035, and I will also need n2, which is y coordinate of this point, and y coordinate of this point is 0.615. So at this stage, now I know the values of x2, y2 and n2, which I am going to use for doing further calculations for stage number 2. So next we will find out calculation of U2 and O2, that is quantities of underflow and overflow formed in stage number 2. So for that I will use definition of N2. N2 is kg of B divided by kg of A plus kg of C in the underflow that is formed in second stage. Kg of B is known to me, it is 12.5. N2 we just got, it is 0.615. So 0.615 is equal to 12.5 divided by kg of A plus kg of C in the underflow in second stage. That is kg of A plus kg of C in the underflow of second stage is equal to 12.5 divided by 0.615. That is kg of A plus kg of C in the underflow is 20.33, which means that the quantity of underflow, that is kg of A plus kg of C for the second stage is 20.33 kg. Now let us get the value for O2, quantity of overflow in second stage. So for that we will use this material balance. Underflow in the second stage plus overflow in the second stage is nothing but mixture in the second stage. So U2 we just got 20.33 kg, M2 is 100 kg, we know that. So therefore 20.33 plus O2 is equal to 100, that is O2 is equal to 100 minus 20.33, that is O2 is equal to 79.67 kg. So in this way, we get quantity of overflow that is removed from second stage. Now in the third stage, we are going to use fresh water, fresh solvent, whose weight is 79.67 kg, whose weight is equal to the weight of overflow that is removed in second stage. So let us continue. So now let us do our calculations for the third stage. In third stage, the underflow in the second stage is contacted with fresh solvent, that is water. The quantity of solvent used is equal to the quantity of overflow that is removed in the second stage. That is SO3 will be equal to O2, and O2 we obtained 79.67 kg, that is SO3. Quantity of solvent used in third stage is 79.67 kg. So now we can find out M3. M3 is just U2 plus SO3. U2 is 20.33 kg. So M3 will be equal to 20.33 plus 79.67, which is equal to 100 kg. Since you are replacing the overflow with equal amount of solvent. So that's why the mixture will have a weight of 100 kg. Then we need, let us find out NM3. NM3 is kg of B divided by M3. Kg of B is 12.5. We know that NM3 therefore will be equal to 12.5 divided by 100, and it is again 0.125. For this particular numerical, this is not changing, because every time you are removing the overflow and you are replacing it with equal quantity of solvent, fresh solvent. So NM3 is again 0.125. Then let us find out, let us calculate YM3. YM3 is U2 Y2 plus SO3 X0 divided by M3. Y2 is 0.035. We have obtained it earlier. X0 is 0 because you are using fresh solvent. So YM3 will be equal to 20.33 into 0.035 plus 79.67 into 0 divided by 100. That is YM3 is equal to 0.7116. 0.7116 plus 0 divided by 100. That is YM3 is equal to 0.007116. So now we know NM3, YM3. Let us move ahead. Okay, so let us use the graph that we had drawn earlier. And in second stage, in the third stage, underflow from stage 2, it is mixed with fresh solvent. And how to show that on this diagram? For that, we need to connect point U2 with S0. So you are using fresh solvent in stage 3 as well. So it will be located at, it will be represented by point S0, which is at the origin. So you are going to connect those 2 points. U2 is now connected with S0. Then we have to locate point M3. It will be located at YM3 and M3. We earlier got YM3 as 0.0073 and NM3 as 0.125. So you can locate over here with the help of NM3, which is 0.125. And now we need to draw a tie line through this. So let us do it. Now M3 is located. Okay, so now we have to draw the tie line through M3. For that, we will use the equilibrium diagram. And then we will first draw a tie line through M3 that is parallel to the nearest given tie line. And then we will adjust its position to ensure that the endpoints of the tie line, they are representing equilibrium concentrations. So if I do that exercise, I get X as 0.006 and Y as 0.12. So endpoint, tie line with these endpoints will be the desired tie line. So I draw a tie line, the desired tie line, and then for this, the one end of the tie line, this end of the tie line will represent underflow obtained in third stage. I am representing that by U3. This end will represent O3, the overflow that is obtained in the third stage. So in this case, X3 is 0.006 and Y3 is 0.012, whereas N3 in this case is 0.66. Now we will use these values for doing the remaining calculations. So now let us calculate U3 and O3, that is quantities of underflow and overflow obtained in third stage. So for that, definition of N3 is used, kg of B per kg of A plus kg of C in the underflow in third stage. Kg of B is 12.5, N2 we just got 0.66. So 0.66 is equal to 12.5 divided by kg of A plus kg of C in the underflow in third stage. That is kg of A plus kg of C in the underflow is equal to 12.5 divided by 0.66. That is kg of A plus kg of C in the underflow in third stage is 18.94, which is nothing but U3. So U3 is 18.94 kg. Let us move ahead. Now we need to find out O3, overflow, quantity of overflow in the third stage. So for that, we will use this material balance. U3 plus O3 is equal to M3. U3 is 18.94 kg. We just got it. M3 is 100 kg. We know that. So 18.94 plus O3 is equal to 100. That is O3 is equal to 100 minus 18.94. That is O3 is equal to 18.06. This is the quantity of overflow that is obtained in the third stage. Then let us go for the final calculation. Fraction of NaOH that is left unrecovered in the sludge in the third stage. So for that, we are going to use definition of Y3 because that will give me kg of C. That's why I am using definition for Y3. So Y3 is kg of C divided by kg of A plus kg of C in the underflow in third stage. Y3 is 0.012. We have got it. And then kg of A plus kg of C in the underflow, which is U3, it is 18.94 kg. So if I use the values, it is 0.012 is equal to kg of C divided by 18.94. Therefore, kg of C is equal to 0.012 into 18.94. That is kg of C is equal to 0.227 kg. Thus, 0.227 kg, the meaning is 0.227 kg, it remains unrecovered in the sludge. So out of 10 kg, we have removed all but 0.227 kg. So 0.227 kg, it is unrecovered. And now we have to express it as a fraction. So fraction of NaOH unrecovered is calculated in this way. So I am denoting it as CUR, C unrecovered. CUR will be equal to kgs of C that is unrecovered divided by kg of C in the original mixture. Kg of C unrecovered is 0.227 and kg of C in the original mixture it is 10. So that is the fraction of C that is unrecovered is 0.0227. And if you have to express it as a percentage, you can multiply this with 100. So percentage C that is unrecovered, it is 0.0227 into 100. Therefore, percentage of C that is unrecovered is 2.27. And that is what we have to report in this particular numerical. So with this, I end my discussion for this numerical. I hope you have learned how to do calculations for multistage cross-current leaching. If you have any doubts, you please mention them in the comment section. And I am hopeful that you have understood how to do calculations in this particular numerical. So with this, I end my discussion for this particular video. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. In my next video, I will be discussing multi-stage counter current leaching, and hope to see you soon in that video where I'll be discussing multi-stage counter current leaching. For now, Have a nice day. Thank you. Bye bye.